The topic of today's webinar is building resilient grids in a changing climate. I think this is very apt in the times we are actually living and facing the situation, and I'll explain to you how. First of all, let me introduce the speakers. So my name is Yogendra Vasishta, and I'm from Melbourne, Australia. And with me, Dr. Waqas Javed is joining from UK. So ladies and gentlemen, it is his midnight there. So thanks in advance to Dr. Waqas Javed. And I again welcome you all for this EA Technologies webinar. This is so nice of you to join this Thursday morning. So welcome everyone to this Building Resilient Grids webinar. I will actually introduce what we have planned to discuss with you today and focus on climate-driven network resilience. And then I will provide what is happening in Australia, what is there in the Australian context, especially the regulatory side, and then give you some few examples from the revenue reset proposals from Australian DNSPs, what kind of proposals they are putting up for resilient grids. And then my colleague, Dr. Waqas Javed from UK, he will be talking about the smart grid innovations. The project EA Technology actually has done it, and also a model, we call it target model, and which is used for reliability analysis. But and you will see how this model can be equally used for resilience modeling in terms of finding out those extreme scenarios. And then I'll let you know that battery energy storage system is one of the solutions for reliability, resilience, resilience in the sense that it becomes a distributed resource. So like decentralized resource. So I'll brief you about it, how we have been involved into that. And as I said, that we will be taking up the question answer session at the end. Please do write your questions in the Q&A box. So climate-driven network resilience, that's the topic for today. And welcome everyone again. I'm just starting this webinar now. And with me, my colleague, Dr. Waqas Javed, has also joined from UK. So resilience is not just climate, but what I'm saying is that electricity grids have always been resilient and reliable, but the question is they have to be more resilient now because a lot of changes are happening, and their changes are happening significant and faster. So, for example, because of the net zero target, all the transport, all the industrial processes heat has to be electrified. So that means the demand, the kind of demand we will see is actually going to increase a lot. So networks have to be resilient to accommodate that growth in demand, high growth in demand due to electrification for net zero targets. And then we are saying AI, and driven by AI is the growth of data centers right here and there, everywhere. Huge loads, and networks have to be resilient for that too. Cybersecurity is no brainer. You know, this is why I'm telling these things. These things are always there, have always been there, but they are not BAU. They are more than BAU. And renewable generation mix, as the coal is retiring, about to retire everywhere, that vulnerability or variability, I should say, the variability in the renewable generation mix for the good reason of net zero transition has to be managed by networks. And all that new solutions we have, they all require the customer's participation and community's participation. Without that, they can't succeed. and networks have to be resilient for that too. And in addition to these, there's a climate, there's a extreme weather disruptions. They are more frequent. They are still a low frequency, but that frequency is increasing or the impact is very high. And every region has a different kind of climate impacts, events, but they are something to be considered as a significant thing which can disrupt the power supply. And they are more than the BAU. I'm just putting up a graph for Australian climate projections, which was from last year, CSRO thing. And as you say, the Australian climate, the warming has, like on an average, it has gone from 1.51 degree plus minus 0.23 in the last century. The sea surface temperature has also gone more than 1 degree. And it has also changed the heat, extreme heat patterns in the land and in the oceans, the rainfall patterns. Somewhere the rains have decreased, leading to the droughts. And some areas, the short-term heavy rainfalls is being noticed. So basically what we're saying is the climate is changing, and that impact, the networks have to withstand all these things. So I'll give you these are the two examples. There's so many examples, but what I'm saying is that just giving one from South Australia, that blackout thing happened because of thunderstorms. And in that, transmission lines went down. So this is not something, this is the infrastructure could not withstand that kind of event. And then, interconnector disconnected and grid collapsed, that part. And then we saw, storms, heavy storms. And then the second example, where we are saying so many, thousands of customers, they were still out of power after 72 hours. So what we are saying, these are those kind of impacts where customers are, because the infrastructure could not withstand, or their recovery cannot happen, people can't access those areas, that can take more than 72 hours. So how the network can actually cope up or provide alternate arrangements for those customers. So when I'm talking about the climate resilience, it is actually to anticipate it, so model it, know it, that what is the changes happening in climate and how it will impact in the geography where we operate the network. And then the infrastructure has to withstand that force. So, like it is like even physically, it has to withstand that force. Thermal, it has to withstand that heat. And then it has to ride through that. And then once it happens, it should have the ability to recover quickly from those hazards. So this situation is, again, I'm saying, when we are talking of resilience, we are talking of extraordinary events, which causes, extreme disruptions, and they are not the same as day-to-day performance issues under normal condition or BAU. So this is where we said one is called reliability and one is called resilience, network resilience. Now, in terms of the solving the issues, there are so many ways we will see in this presentation throughout, but I'm just sharing one news where, it said VPP helped save the grid during heat recently. So basically what happened is that because the VPP, the heat, extreme heat leads to the peak demand, very high peak demand for a short duration. And so VPP with the storage facility could actually supply some demand. And with the demand response and load control of DERs, actually could take away some of the flexible load out of the that time zone, or shifted the load. So you can provide extra energy through the storage, through VPP, and take out some, control some of the loads, to and make it as a flexible load. This in Australia, there's another situation where we get minimum demand, and we were talking about minimum system loads, which is again, like we have to manage. So the DER and CER, distributed energy resources and consumer energy resources. Consumer energy resources, when I'm saying behind the meter resources, solar panels, batteries, and EVs. So all these things, when they are orchestrated or coordinated through third-party aggregators, and they are playing in the flexibility market, they can be part of the solution of network resilience, and they are already part of the solution for network management, the voltage management, and the reliability management. Now, what is happening in terms of the regulatory things? That Australian Energy Market Commission has made a final rule, and which is saying that, now AER will accept in their part of revenue receipt submission proposals, this resilience expenditure proposals separately, because it was realized that it is not the same as business as usual, and there has to be a different, thought process to approve. Of course, this is there's a way to go, because for reliability we have set metrics and matrices and saying, okay, all right, this is SAIDI, SAFE, KD. And now for resilience, what are those matrices? And then how do we say what is enough, adequate, what is too much? You can spend billions of dollars and underground all the network, but that may not be the optimum. So it has to go a long way to actually develop that clarity, that resilience expenditures, what are reasonable expenditures, what actually are more effective, and what are the matrices we have to look for. So AER is developing those guidelines and matrices where you can say, you can then compare, like we do SAIDI and SAFE, who is doing what. Like on the same basis, we have to do matrices for resilience, like system performance, operational performance, those matrices under those extreme weather conditions, how the network did, what it should do. But at the moment, those things are not available. So in the interim, the value of network resilience is linked to value of customer reliability. Value of customer reliability has been in use in Australia for a long time. This is used to even for the economic justification of any innovation or any upgrades. So at the moment, AER's interim VNR approach is just saying if it is the outage is 0 to 2 hours, use the standard VCR. And if we are expecting that outage to the customer will go beyond 12 hours, then you multiply that by 2, and beyond 24 hours, multiply that 1.5 and kept to a level. So basically, this is just an interim thing, the value of network resilience used to justify the expenditures, but I'm sure there will be more new resilience matrices and new ways of actually assessing the economic business case for the expenditures on network resilience in the times to come. I've just taken a few examples of, especially from Victorian DNSPs who have submitted their regulatory proposal, and their determination will happen by end of this year for the period of 2026 to 31. And just to show you an example, what kind of network resilient work we are thinking and we are talking about it. So if I take the Power Core examples, and these are all public documents. So they basically for resilience, they're saying prepare, adapt, and respond. And what sort of things they're saying? If it is a flood area, okay, taller poles. If it is, like bushfire area, it's a poles have to be more fire resilient. If it is remote communities, microgrids, and then enhanced climate modeling to forecast where things will happen. Because even if you can forecast, we can actually put the resources in advance there. The trucks can be there just waiting for things to happen to provide very quick restoration. The battery support for communication networks so that that information is maintained. Mobile emergency response vehicles and community support and all those kind of things which they are proposing for as part of the network resilience. So they're basically asking, for network hardening. So some part is actually hardening so the network can withstand and it doesn't fail. And then, or it can actually isolate it quickly and it can actually reconfigure itself. All those sort of things. So network has the ability, or it can have a decentralized power system for some time. And then there's a community support so that we actually provide the quicker response in the community. And there is, like in terms of extreme events like flood and everything, we can have public safety power shutoffs, so that everything is shut off. In terms of high bushfire danger zone, we can actually shut off the things and depend on solar and battery systems, microgrids, standalone power systems. So there can be many solutions like that. I'm just showing a few examples. Similar sort of thing from United Energy, that network hardening and adapt by taking a future-proof, no-regret approach to a business-as-usual operations and response. So United Energy, again, on network hardening and community support. So it's basically providing that community, which is going to be out of power for a few days, where even the trucks can't go and things cannot improve, or power line have fallen on the ground to the ground. That taking the community into confidence and provide them some kind of support. Those things are very important. Plus, improving the infrastructure. I mean, we were talking just before this webinar that if extreme heat happen, that if we have taken the maximum temperature as 45 in the product design, maybe tomorrow we have to use 55. I mean, so even the products which we use, or the selection specifications might change in some cases. Now the AusNet actually has asked for 226 million in the next 5 years, and in network hardening, you can see undergrounding of some part, covered conductors or insulated. Hardened poles, reclosures to reconfigure the feeders quickly. Standalone power systems, community hubs, mobile generation and batteries, emergency vehicles. So all those sort of things are there for preparing to withstand and prepare and actually recover from climate-driven things. I mean, I'm not going to that, but basically, this is saying what are the things we are doing to prevent, what they're proposing to prepare to respond in terms of the network and communities, and when something happens, what is the process to respond and recover from those extreme events. So these are basically disruptions to the network and how the network can ride through and recover and maintain the continuity of supply. And I'll now hand over to Dr. Waqas Javed to go through the next part of it.
Thank you, Dr. Yogendra. I would just like to take the opportunity to introduce myself a bit. I'm joining from the EA Technologies UK team. I'm a team lead for network reliability in net zero transition team. Thank you very much, Yogendra. That's really helpful framing of the regulatory and strategic momentum building around resilience. And it's clear that responding to climate risk isn't just about high-level policy, it's about what we do differently on the ground across our networks. So in this section, I will take you through a series of smart grid innovation projects from the UK that were specifically designed to uplift network reliability and resilience, in some cases under challenging rural and low density conditions, and in others through automation or targeted investment strategies. So we will explore how distribution network operators have, like in UK, we call distribution network operators, as compared to Australia's, that's called DNSPs there. So just bear with me around that terminology. So we'll explore how DNOs have used data simulation, practical engineering to identify vulnerable areas, reduce customer impact, and build a stronger foundation for resilience. So even where full-scale reinforcement may not be feasible. So these examples are intended to adaptable and thought-provoking. So with lessons that are very much relevant to Australian DNSPs. So as you look to prioritize low cost, high impact interventions in the face of increasing climate uncertainty. So that I'll go through that. So let me begin by zooming out from the projects. First of all, the biggest question facing networks today isn't just what technology to trial. It's how to build resilience into strategy itself. So in the UK, we have worked with DNOs to help them build forward-looking innovation strategies. But this wasn't about shiny trials of different things. It was about building a structured, justifiable approach to tackle future challenges like climate change, system electrification, DER growth, and of course, resilience. So what actually we did, the particular project was about answering one core question: where should a DNO invest in innovation over the next 5, 10, or 20 years to deliver customer value, regulatory compliance, and system resilience. So our role was to support the DNO in developing their innovation strategy, and we worked across technical, regulatory, operational, and stakeholder layers to build a roadmap aligned with the Rio ED3 framework. So Rio in UK is kind of a regulatory uh, framework that's called revenue equals to incentives plus innovation plus outputs in electricity distribution. So they renew, they look into it after every 5 years. So we are entering into a third price control right now. So that's the framework is developed by Ofgem, the UK's energy regulator, as you have in Australia, AER or AEMCs are doing that. So that's kind of thing. So in this project, we identified key future pressures from volatile demand to storm risk and aging infrastructure, and mapped out capability needs which needs to be addressed them. So what emerged was a strong alignment between resilience and the need for innovation to be both proactive and evidence-led. So through that work, several recurring themes became clear, and I think they resonate directly with the direction Australian DNSPs are now taking under AEMC's resilience rule, which is like climate adapt. So first is like climate adaptation and extreme weather. So innovation cannot just be about DER. It needs to support infrastructure that's storm-proof, bushfire resilient, and heat wave ready. The second one is DER uncertainty and electrification. So we need tools that can keep up with changing customer behavior, whether that's a sudden shift in rooftop solar, the rollout of EVs, or localized demand spikes. And then dynamic flexible investment planning, which is like static planning approaches are no longer enough. So networks need to plan dynamically based on real world data and predictive forecasting. So, and most importantly, we identified three critical enablers. Once you'll see reflected in the case studies that I'll follow in the next few slides. So the first one is operational agility, which is technologies like automation, LV monitoring, and real-time switching enable faster, smarter responses to fault or overload. Then data-driven risk forecasting, modeling SAFE and SAIDI exposure or voltage headroom under future weather and demand scenarios is essential for justifying resilience investment, and then localized low-cost resilience measures. We are talking about solutions that can be deployed at a scale like pre-fault detection, autonomous LV devices, and smart DER controls. So these aren't multi-million-dollar schemes. They are tactical, targeted actions that align with AEMC expectations. So when we think about resilience, especially in the context of increasing extreme weather events, one of the most urgent questions is how quickly can we restore supply after a fault? So traditional restoration methods, especially on meshed LV networks, are slow and manual, often relying on field engineers to isolate faults and reconfigure backfeeds. So, but during storms or floods, access is limited and customer outage duration can spike. So this is where autonomous recloser automation at the LV level offers a high impact, low cost resilient solution, giving the network the ability to self-isolate faults and reconfigure supply paths without waiting for intervention. So this was a project this we did where we trialed autonomous LV switching devices that isolate the LV interconnection when energized from one side only and reducing fault feedback and detect voltage restoration and enable stage restorations as well. So I'll walk you through those that what actually is one of the scenarios that we built. So let me walk you through a real world scenario where the automation approach supports grid resilience during storm related faults. So here we are looking at if you see the first figure here, the system is operating normally with supply from both sides. Then in figure 2, we simulated a fault at HV fault on one side and the upstream breaker trips cutting supply. The LV link still holds, but so if you see this LV link is still holding, but the risk here is uncontrolled backfeed or burnout of LV connectors. So what it do is do the first stage restoration from the other side. So the recloser device powers up from the cable side and recognizes it's only energized from one direction. So it trips it open within 2 seconds to safely isolate the section. Coming to the second stage restoration. So the faulty section is isolated and the healthy side begins to restore supply from that side. And then the final, if you see the last final restoration is like the fault has been cleared and the LV recloser returns to its normal state. So this type of innovation doesn't require radical infrastructure overhaul. So it's a firmware level upgrade to existing LV switchgear, making it both affordable and scalable. So for Australian DNSPs, particularly those managing bushfire prone areas, cyclone corridors, or rural feeder ends. This approach enables real-time storm resilient reconfiguration and is fully aligned with AEMC's resilience expenditure expectations. Now moving to another type of a project. We have talked about restoration and automation so far, but let's take a step further upstream and ask, what if we could spot the fault before it happens? So that's what's the pole site project set out to prove. In this trial, we developed pole top smart sensors that continuously monitor the health of rural LV overhead lines, the parts of the network most at risk from wind, storm, and vegetation interference. So the device capture waveform anomalies that indicate pre-fault behavior, things like conductor galloping, arcing, or damaged insulation. So these insights are streamed back in near real time to network operators who can respond proactively, often resolving the issue before customers even notice a problem. So for DNSPs, this approach is ideal for storm corridors, bushfire zones, or long feeders where patrols take time and customers are especially vulnerable. So it's a scalable, field-proven example of smart grid innovation delivering practical resilience outcomes. And critically, it aligns again well with the EMC's emphasis on targeted, justifiable, and customer-focused resilient investments. So here is one example from this project. So this case comes from January 2024 during storm Isha that hit in UK. So where a widespread storm with high winds that impacted several regions. If you see this top left figure, Here it's at 2023, a pole-mounted device on an LV overhead feeder a pole side device recorded a waveform disturbance between L1 and L3 phases, indicative of either arcing, clashing, or insulation failure. The event was flagged as a credible pre-fault, and the location algorithm triangled three possible sites along the syntax feeder, all associated with the bare conductor spans. So a few days later, field crew confirmed that two poles had snapped and grounded just outside the spotted areas. So the on the if you see, the pole has been snapped on the right hand side of the figure, right? So fortunately, the issues was resolved already under repair by time inspections occurred. But the fact that the event was detected, localized, and matched with the real physical damage makes this case a resilience through smart sensing. So imagine deploying this in bushfire prone or flood affected rural areas across Australia. This is actionable early warning at scale. So it gives DNSPs not just fault visibility, but a defensible evidence base for resilience expenditure. So another project regarding resilience. So this project called FREE, which is Fuel Cell Renewable Energy Equity, looked at how fuel cell combined heat and power systems can be used as a resilience asset, not just a decarbonization tool. So the primary aim was to analyze whether community scale fuel cells, when deployed in apartment heavy LV networks, could help reduce peak loading and defer reinforcement. So we modeled 8 scenarios using or transformer tool that's in built tool in EA technology, assessing different uptake rates and load profiles across representative UK urban LV networks. So the results showed that deploying fuel cells led to 15% reduction in load related expenditure, about 80 kilowatts of local load offset per feeder, and strong benefits in delaying the need for costly upgrades, especially post 2030. So, but what makes this relevant to resilience is that these system can operate during outages, providing both electricity and heat to vulnerable communities. So they are particularly suitable for areas where batteries or solar alone might not be enough and where rooftop space is limited. So this slide shows the key outputs from our FREE project, where we use our transform model to evaluate the effect of fuel cell deployment on LV network investment. What you are looking here is feeder one, a representative, which represents urban LV feeder supplying one apartment block of 75 flats plus 10 additional houses. So the aim of this modeling was to understand whether deploying communal cells fuel cells in high density locations like multi-occupancy flats could help manage the growing pressure from electrification, EV charging, and heat pump adoption, and reduce or delay the need for reinforcement. So the graph on the right shows cumulative total expenditure under different deployment scenarios with and without fuel cells on this particular feeder. So the green line is the base case, no fuel cells, just EV and heat load growth. And the gray, purple, and blue lines show increasing levels of fuel cells penetration. So the findings, the key findings from here is the investments is delayed. In the base case, you see investment triggered early, often due to voltage rise or thermal constraints within fuel cells. If you can see this, it's an early expenditure. So with fuel cells, those constraints are reduced, pushing investments out by years. So the total expenditure by 2050 drops from around 89k pounds down to 46k pounds, a saving of over 43k pounds in this one feeder alone. So hence, with two large fuel cells, we reduce cumulative total expenditure by nearly 50%. And this doesn't even factor in the resilience values, such as fuel cells continuing to operate during outages and supporting customers off-grid when required. Now, let's take a look at strong international reference, one of our New Zealand's projects, where larger electricity distributors operating in region increasingly impacted by storms and weather variability. So the goal of this project was to support New Zealand distribution services providers in shaping future-ready network transformation roadmap by identifying data and visibility gaps and aligning investment strategies with climate resilience, DER integration, and customer impact mitigation. So EA technology helped them benchmark UK and Australian approaches to smart metering, LV monitoring, dynamic ratings, and flexible enablement. So the biggest takeaway is that the smart meters alone are not enough. In the UK, we have seen clearly that when you combine smart meters with strategic LV monitoring, you get much more than just load visibility. You get the ability to detect degrading asset, target reinforcement, and just resilient spend. So New Zealand distribution operators roadmap now includes developing a common data model, investing in dynamic asset ratings, exploring how to participate in future flexibility markets. So they are also taking steps to identify and protect vulnerable customer clusters, which aligns perfectly with emphasis on equitable resilience planning. Moving on to the next one, we did one project earlier with one of the DNSPs in Australia, where this project focused on how DNSP should strengthen its LV network resilience while managing future pressure from electrification and DR growth without relying solely on reinforcement. So using the transform tool that we have, we worked with their planning and strategy teams to simulate scenarios involving high uptake of EVs, heat pumps, and solar PV, all of which are forecast to significantly impact load profiles and voltage stability at the level. So the modeling also evaluated demand side measures, including time of use tariffs and DSM schemes to determine their effectiveness in reducing peak demand and determine investment. So their results and analysis shows that the modeled investment saving achieved under different time of use and demand side management strategies across four AEMO scenarios like net zero 2050, step change, slow change, or hydrogen export. So what's clear here is that in more progressive scenarios, particularly step change and hydrogen export, these strategies deliver significant reduction in required reinforcement expenditure. In the step change scenario, high time of use uptakes saves nearly $100 million in investments, and even medium demand side management uptake results in 60 to 80 million dollars of avoided reinforcement in multiple scenarios. So importantly, these savings directly support resilience goals. They reduce peak demand on LV networks during critical periods such as heat waves or storm related loading. They defer infrastructure upgrades, freeing capital for targeted risk, reducing resilience investments, and they rely on customer behavior and tariff signals, not physically built, but making them low cost, scalable, and regulator aligned. So looking into this one, it's about the demand side management on typical LV feeder during a winter weekend. Projected from 2038 to 2046. Each line represents the total feeder demand across a single day in a given year. The highest peaks, as you can see, occurs between 6 to 9 slot, which aligns with residential heating, lighting, and cooking loads. So what if we model here is how with demand side management in place, customers can shift or curtail their non-critical load during these peak hours. So the result is flattened and reduced peak demand curve, which directly improves resilience. And then obviously, here's why this matters for resilience is first, a lower peak reduces the chance of LV falls or overloading during heat wave storms or unplanned outages. Second, by reducing stress on the feeder, we are also extending the life of existing assets, avoiding failure during climate-driven stress events. And third, the given DNSPs time to make better targeted, lower cost investment decisions, not just react to emergencies. So coming to the in the first part, we have looked at a series of smart grid innovation and modeling approaches that may help DNSPs enhance resilience, whether by managing LV network constraints or automating restoration or detecting faults before they happen. So these tools may help network act proactively, not reactively, and in ways that are scalable, cost-effective, and increasingly aligned with AEMC resilience agenda. But when it comes to justifying where and how to invest, especially under pressure from climate volatility, regulatory scrutiny, and limited budgets, so we also need a way to understand which parts of the network pose the greatest risks to reliability. Where can targeted investment have the biggest impact on customer outcomes, and how do we quantify this in terms of SAFE and SAIDI to support expenditure cases? So that's where we move next into the realm of reliability threat assessment and investment optimization using a tool called the target model. So I'll just quickly give you a brief introduction about what the target tool is. It's a target model. It's a simulation tool that we developed to help electricity networks evaluate and improve their reliability and resilience performance, especially under increasing pressure. Obviously, climate, limited investments, and all that. Um, so it runs. So this target is unique. It brings together network topology, asset condition data, and operational logic, and runs thousands of simulations using sequential Monte Carlo technique to understand how random asset failures would actually play out across the network. So I'm not going into detail of that. We'll just take a look what we did with this quickly, as we are running a little bit short of time. So some examples of resilience analysis that we have studied on the real network. So as a part of a wider assessment, the target model was used to simulate and analyze reliability performance across a group of 18 HV feeders with very different characteristics. So from that portfolio, two contrasting examples are selected to demonstrate how the model supports resilience-focused investment decision making. So we have selected feeder X, say it has smaller feeder, 10 distribution substations, and feeder Y, which has larger feeder with more than 100 distribution substations. So what it includes mostly the ground-mounted distribution transformers, mainly underground cables, and it's a pretty much simpler network with just 10 switches on that. So target tool runs thousands of fault scenarios on feeder X to evaluate reliability profile under this current condition, and it counts as these results where the customer interruptions or customer minute lost that we usually use in UK terminologies, where SAFE and SAIDI in Australian terminologies, and we can see that the model helped to identify that which substations are most affected. In like you can see, substation 3 contributed most to customer interruptions, while substation 2 had longer restoration times and contributed disproportionately to the customer minute loss. So interestingly, the number of faults simulated per year was very low, but because of the feeders configuration, a single failure often resulted in long restoration times for large proportion of customers. So this reinforces that resilience isn't just about fault rates, it's about response and recovery as well. So these insights gave us the basis to test investment scenarios in the next step. So including the impact of adding switches, configuring the open point, or introducing automation. So to see how these could reduce customer impact and justify resilient expenditure. So this we have identified two substations which are mostly having the most customer interruptions or highest customer minute lost. So what we can do is, what we did is by after identifying that substation 2 as the location with the highest customer minute lost, we tested a targeted intervention to see how much improvement could be achieved. So using the target model, we added a single additional switch at a specific point on the feeder. So just before the section that feeds substation 2. So this was a low cost intervention, but one that had a significant impact on restoration pathways during fault conditions. So what you see in these schematic below is the updated network with the proposed switch highlighted in the red. So this small change allowed the network to isolate faults more effectively and restore supply to substation 2 much more quickly, even in cable failure scenarios. Right, and you can see on the right hand side, the SAIDI has improved from 54 to 23. Like it has gone a 57% reduction in the customer minute lost there. Then in feeder Y, which is a longer feeder, we did the analysis, same analysis. Again, there were some other uh, uh, mm, you can say impacts on the network, where you can see there's quite a lot of customer interruptions or customer minute loss, or SAIDIs, APs were quite high in that case. So if we analyze that, so after establishing the overall reliability performance of feeder Y, we then use the target model to drill down the individual line segments across the network. So if you can see that in the total number of interruptions by asset or total duration of interruption by asset, there is one line which is coming as in prominent, which is line 237. So this is the kind of insight that often gets missed in average of feeder level assessments. With this level of granularity, we were able to recommend line 237 as a priority candidate for targeted investment. So where that's refurbishment, automation, or structural reinforcement will help to reduce the outages. So by applying this asset-specific lens across the whole feeder, the DNO could create a ranked list of critical interventions, enabling a data-driven, optimized resilience investment plan, fully aligned with customer impact and regulator expectations. So what we did, if you see line 237 is an overhead line running across agricultural and land supplying small dispersed settlement. So the data available didn't include the specific cause of faults. So we didn't know, for instance, if the primary issues were vegetation, pole condition, or conductor damage. That's where local engineering knowledge would typically provides critical insight. But even without those details, the target model allowed us to simulate a reinforcement scenario. So where the probability of failure was reduced through some form of targeted intervention, tree cutting, circuit upgrade, or automation, for example. So when we ran the simulation with the change in place, like in reducing the probability of failure, so outage duration dropped significantly, and the total number of interruption also fell. So this improvement was enough to move line 237 out of top 10 worst performing assets, meaning that with one relatively small investment, customers' reliability improved considerably. So this gives asset planners and investment teams the ability to quantify both risk and reward, enabling them to assess whether the cost of work is justified by the improvement in service quality. It also empowers collaboration between modeling outputs and local engineering knowledge. So a critical combination for effective resilience planning. So it also gives you the output in visual form as well. So concluding of this reliability analysis. So I want to draw the connection between everything we have explored, whether it's identifying high SAIDI, SAFE, evaluating switching interventions, or understanding how customers are impacted and what actually means for building a more resilient grid. So resilience isn't a separate track from reliability. It builds on some same foundation, but stretches the thinking toward how well our networks can withstand, adapt to, and recover from like shocks. So the kinds of insights we gain from reliability modeling is like those I have shown through you some UK examples are helping networks prioritize smart investments, reduce risk, and justify resilient spend with quantified outcomes. Like resilience, one of the most important roles of reliability modeling is that it helps us uncover vulnerabilities that exist even before a crisis happens. So areas with high interruption rates or long restoration times under normal operating conditions are often the same places that struggle most during extreme weather events or major faults. So understanding those vulnerabilities through SAIDI, SAFE, and asset performance is the first step toward improving resilience. So when data shows that a particular substation or circuit consistently causes high customer impact, even if failures are infrequent, so it's a red flag for resilience. So these are the locations where extreme events will likely cause the most disruption and where interventions can yield disproportionate benefits in terms of outage prevention or faster recovery. Then another strength of this approach is that we can simulate stress scenarios. For example, we can increase failure probabilities to reflect extreme heat or storm conditions to reduce excess speeds to reflect post-disaster constraints. This gives planners a way to explore what would happen under more extreme conditions and test whether the network would still function and how long restoration would take and what gaps needs to be addressed. So that's how we can include DERs into the scenarios and make more analysis on that. So yeah, I'll hand over to Yogendra for further.
Yeah, thanks, Vikas. Battery energy storage system, we have seen that, as business as usual and resilience, standalone power system, microgrids, distributed generation, this is part of the solution. Definitely, I just wanted to let you know that, EA Technology developed the national guidelines for distribution network service providers, owned BES, for ENA Australia. And I was there part of that project, and there's a working group from all the DNSPs, and these guidelines are now available. So if you go to ENA website, this is a new asset class adding to the distribution network asset management. So basically the question was, how to harmonize that information in terms of functional requirement, technical requirement, in terms of risk assessment, fire and safety protocols, handling, storage, all the change management it comes with. So that guideline is now available, which EA Technology has worked with all the DNSPs under the ENA banner. And just wanted to let you know, this is part of this, resilience solution. Anyway, and there may be a few more polls which Callista will put. Please do provide your response. We will be there. There is a EA conference coming up in Christchurch from 9 to 11 September, and I'll be there. And Dr. David Mills from UK, he will be there. Thomas White from our Brisbane office, he will be there. So we will definitely would like to meet you if you are there attending this conference. We will be there. So EA Technology will have a stand there in the exhibition area. So stand number 31. Definitely would like to have the chat and discussion about, those sort of things which EA Technology does in the area of, future network consulting or net zero consulting, and also in terms of LV visibility and network modeling, and those kind of things which we provide or we offer solutions and advisory. Now, as I said, the Q&A sessions, and we will try to send you the recorded part. But quickly, I can ask just for 1 minute from Dr. Wakas. You referred as a transform model. Can you just quickly tell what that model is?
Yeah, so that's transform model is basically model your future scenarios build on from, like, we in UK we have got DFS, where we can take the future loads capability that we can integrate into our system and see, okay, what variations can happen in future and how that can impact the network capacity, network on the network, how it will the powers flow and stuff like that. So that's basically, it's about the transfer model.
So basically what I'm understanding is that transfer model is actually not exactly the digital twin, but it is a network representation in a parametric model, and then we can run all the scenarios we want to.
Yes.
Yeah, so that's good.
Yep.
And we are going to end this thing, and we will take up your question from Q&A and send you those answers with the recording thing. Just one more thing. In UK, Dr. Bokas, what is the main climate concern?
So main climate concern is storms and hurricanes. That's hitting recently. We have got recent storms this year as well, like two or three. That was quite at very high wind speeds, and they so that's the main concern here at the moment.
And have we seen any net like a infrastructure damage?
Yes,
Like
yes. So as we were talking about the rural areas like conductors, the poles have fallen down. So yes, that there were quite longer outages on those areas.
so, ladies and gentlemen, thank you very much for attending this webinar. We will be there in Christchurch also, and I'm here in Melbourne. Our team is in Brisbane, and EA Technology head office is in UK. We are all there to to have a chat, to organize the meetings, to to come and discuss with you if there is anything which you would like to. And thank you very much. Thank you all.
Thank you so much, guys, for attending the webinar.